trivial character. If you take the trivial character, then bnn1, then you can express it in terms of the hypergeometric Bernoulli numbers. So this is pretty easy to calculate. That if you take chi equals to 1, this bnn1 is simply the sum of this generalized these hypergeometric Bernoulli numbers were introduced by Howard. And if you take n equals to 1, the chi is 1, n is 1, then you get back the classical Bernoulli numbers. So n is 1, chi is 1, then you have these classical Bernoulli numbers to get back. So it says generalization both in the n front as well as in the twisted by a Dirichlet character. Now we have this for classical Bernoulli, generalized Bernoulli numbers, b and chi's. There's a very nice relationship with respect to the Bernoulli numbers, generalized Bernoulli number bn a over f. So f is the conductor of this character that you are taking at it. There's a nice expression is there. This is a classical case. The relation between the generalized Bernoulli numbers and the Bernoulli polynomials is very well known. So this is a very famous relationship, and we can get back this classical one in our terminology also. So this is a proposition that if chi is a Dirichlet character of conductor f, then you take any n natural number, and for any positive integer n, bnn chi you can write in terms of bnn a over f. So this is exact generalization of the previous one that you see the classical ones. So we get back this relationship between the generalized hypergeometric Bernoulli numbers and hypergeometric Bernoulli numbers in this way. It's not difficult to prove these things, not going into any of the proof. A nice corollary comes out from there is that b and n chi generalized hypergeometric Bernoulli numbers in terms of hypergeometric Bernoulli numbers. So these are hypergeometric Bernoulli numbers, and this side you have the generalized one that we have introduced. And so if you want to write it more cleanly, then this is the expression that you get. This is simple corollary from here. And the corollary, the proof is pretty easy, because you just go back to the definition, bnn x t to the bottom. This is the definition, and then you express this one in the expand this exponential function and write it into sums, collect the coefficients here, compare the coefficients on both sides, and you will have the relationship. Okay, the proposition has to be used. So these are not difficult to prove. So this is about, we have studied few more properties of these Bernoulli numbers, the generalized hypergeometric Bernoulli numbers, but not going into that one. So similarly, now the next thing you can do is to define the polynomials. The numbers have been defined. Now you can define b n n chi x, where you look at this genetic function where e power x plus at will come here, just like the classical one. And then you will collect the coefficients. They will turn out to be this generalized hypergeometric Bernoulli polynomials here. And as usual, if you take n equals to 1, you get back the generalized Bernoulli polynomials. And if you take chi equals to 1, you get back the hypergeometric ones. Okay, so this is a generalization from both sides. And if you take chi equals to 1, n equals to 1, you had seen that in the previous case, but for Bernoulli hypergeometric Bernoulli numbers, we get back the classical Bernoulli numbers. And if you take chi equals to 1 and n equals to 1, just put it here in the definition, you get back the classical Bernoulli polynomials in terms of the classical Bernoulli polynomials. So the generalization is perfectly fine, and we can have this nice property which will give us a nice corollary here. I'll come to that one. This identity that if you take x plus y, then in fact you can write in terms of x, where k equals to 0 to n, these binomial coefficients will come up here. And if we sub in x equals to 0 here, and we put y equals to x in the previous in this proposition, that this proposition, if we put it there, then use that. So then we can write these Bernoulli polynomials, the generalized one, in terms of Bernoulli numbers, just like the classical one. So this is another result that you would expect to hold when you define this generalized Bernoulli polynomial. So that's also true in this case. And now this has some nice relationship with other interesting numbers. So you look at these Starling numbers. The genetic function of the Starling numbers of the second kind is this: e to the power t minus 1 to the power L by L factorial. So these are the Starling numbers that come out of the second type from this generating function. And our generalized Bernoulli polynomials are in fact, this is typo is here. This should be Bn, and this should be sub here, n minus k chi. So these Bernoulli polynomials here can be written in terms of these generalized Bernoulli numbers as well as the Starling numbers here. And here XL is the the falling factor here with x not equals to 1. So this is another nice relationship that one gets. And then you will be asking that whether these generalized hypergeometric Bernoulli polynomials are apple or not. So that means this nice relationship with respect to derivative, the usual derivative that ddx of bn and chi x is n times bn n minus 1 chi x, whether this holds. So when such a relationship holds, we call these polynomials are apple. Because this relationship can be used for many deriving many other nice properties. So in this case also, it happens that for any n bigger than or equal to 1, if we take the derivative with respect to x of these Bernoulli polynomials that we introduced, turns out to be that n comes out here, and this n minus 1th Bernoulli polynomial is related by that. So there is a quick proof of that one. So if we take the derivative of this bn n chi x t to the power n, so then t comes out here, and this t power n plus 1 is here, and factorial n plus 1 come here. And so this is n bn n chi x t to the power n factorial n. Then you compare the coefficients and the result will follow. So this is a simple derivative relation, but this apple relation this apple, some polynomial becoming apple, seems to be a quite interesting one, and it helps in quite a few things. So now these generalized Bernoulli numbers and polynomials that we define, they satisfy nice recurrence relations, which another thing that you would expect if you want to define something new, that is recurrence relations should hold. So if you write Sn equals to a equals to 1 to f chi a power n, this character sum, and Sn x is a plus x to the power n, chi a plus x to the power n, a equals to 1 to f. Is a character I'm taking with conductor f. Then this is a proposition that we prove that if we take this for n bigger than or equal to 1, b n I chi f n plus n minus 1, and you take the sum of this Bernoulli numbers, generalized Bernoulli numbers that we are giving it with this binomial coefficient here, and we get Sn back. This is a nice recurrence relation. And in terms of, so this is for the Bernoulli numbers, and the similar relationship hold for the Bernoulli polynomials. So this is the recurrence relation that it holds. And if you take n equals to f equal to 1, you recall that this is the classical one, that the recurrence relation that we know for classical Bernoulli numbers and Bernoulli polynomials. So this is simply a generalization of that one in terms of characters, the generalized one that we have defined. So it has nice recurrence relations, and from the recurrence relations, you can get the determinant expression and other properties which I'm not going into. So, and if you take chi equals to trivial character with conductor 1, then that first recurrence relation that you prove is simply the classical, the n plus n choose n b n I1 is 0, which is which also you expect that in the class, just like the classical case. Okay, so these are the few properties that I mentioned here for you. The paper, one can, if one is interested, one can look into the paper. Quite a few more properties have been proved on the line of classical studies that people have done it. And the next project will be to really look into the zeta function associated to these generalized hypergeometric Bernoulli numbers and polynomials, and define that and try to see those properties as the some literature that I had mentioned to continue the further the study of these generalized hypergeometric Bernoulli numbers and polynomials. So let me close in my presentation with some of the calculations of these particular numbers that we have introduced. So first few, it's, as you can understand, it's not easy to really calculate these numbers. There's quite a few variables are there. So if we take n equals to 0, b and n chi is simply s naught. You remember Sn in the character sum that I had defined. F is the conductor of that, f to the power n. And if we take little n equals to 1, then it is s naught by n plus 1, that one can find out from the relationship that we had, the recurrence relation, s1 by f to the power n. Similarly, for if you take n equals to 2, so we are fixing n here and then n equals to 2. So this is the expression that it comes out. I'm going only up to 2. And now bn0, the classical one is 1, and bn1 is minus 1 by n plus 1, bn2 is 2 by this thing. And there is a relationship that bn chi, nn chi is in terms of this bn case. As you see before, we are trying to calculate this one. So if we know this one and the expression here, then we can calculate bn0 chi, bn1 chi, and bn2 chi. These are already known things. And we use this relationship that we have proved, plug in there, and then one can calculate. So that's when n is 1 and chi is not the trivial character, as s naught is 0. So you can go back, b10 chi is s naught by f to the power n, since s naught is 0 in that case. So it is the first one is 0, the Bernoulli, first generalized hypergeometric Bernoulli number, if you fix this little n, and it will be s1 by f. It's easy to calculate s1. And b12 chi will be minus s1 plus s2 by f. So these are a few of the, I mean, in the paper we have calculated few more. It becomes more complicated if you go on increasing this indices, and it's not easy to calculate. But the further study will be to really look into whether these generalized hypergeometric Bernoulli numbers and polynomials do come up naturally if we generalize the hypergeometric zeta functions. And that is the next study that one will be interested in. So I close in here and thanking you for your patience. And if there is any suggestion or questions, I'd like to.
Thank you, Professor Kalyan Chakravarti. And, your talk is quite opt on today as a very pious day, the birthday of Ramanujan, that is the National Mathematics Day we are celebrating. And the topic which you have chosen, the Ramanujan was very fond of Bernoulli numbers. And, his first paper, which was published in Journal of Indian Mathematical Society, was on Bernoulli numbers. So basically he has started his work with Bernoulli numbers. So I think your talk is a tribute to that genius mathematician. And thank you for choosing this topic, which is quite relevant to today's celebrations of National Mathematics Day. And I think the hypergeometric Bernoulli polynomials or numbers which you have taken, and then you have shown them to belong to the category of Apple, and automatically when we have taken them belong to the Apple category, then there are various properties, there are various options automatically open, being them like making them quasi-monomial and all those things. And then there are further studies also for maybe for your group or for other groups also, which we can take from your talk. That is the most important thing is to see the combinatorial aspects of this new hypergeometric Bernoulli numbers, because whenever we see some numbers, of course we are not that quick in analyzing, but I wish if Ramanujan would have been there, then he would have got some relationship between the numbers which you have just now illustrated in your talk. And also I think there are possibilities of considering the zeros of these polynomials, and I'm sure that there will be definitely there will be going to be very interesting researches in this topic which you have chosen today. And as you mentioned that you will be going to relate something with the zeta function, So I am certain that the research which you have initiated, and I wish that you do more in special functions now. Thank you very much, Professor Kalyan Chakrabarty, for very motivating and a talk which is opening new paths for in so many directions. Thank you very much.
Thank you, ma'am. Actually, it's not easy for me. I'm not, all of you are specialists in special functions like Professor Pathan, and all of you are sitting there. But I chose this one because, as you pointed out, that, Bernoulli numbers, and, there are most of the audience who will be looking at some. So as you were mentioned, I really tell the people who are interested, so carry on this study, and there are plenty of things to really still work on these things. So carry on with that one, as I have gotten into many, many administrative jobs now. So I don't know how much time I will be able to figure out, but it is really good, ma'am. I mean, you are an expert in this area, and really carry on this research.
Yes,
thanks a
thank
lot.
you. Thank you. If anyone has any other discussion he or she want to discuss with Professor Kalyan, then he or she is welcome. And if not, then I think I invite Dr. Dilip to formally thank Professor Kalyan Chakrabarty for his talk. Dr. Dilip, are you here?
Yes, ma'am, I am here. I am just seeing whether Michelle Wadsmith has joined. I don't know. Professor Michelle?
I think first you should thank Dr. Kalyan Chakrabarty.
Okay. Professor Kalyan, thank you very much.
Yeah, I'm happy that, I'm happy that even Komatsu Takao is there, and he liked my talk. So that, that's very nice. It's a good, thanks a lot, Dilip. Thanks a lot, ma'am.
Professor Kalyan is a regular speaker of our programs. So
yes.
So I am this time also I extend our sincere thanks to Professor Kalyan for once again motivating our students as well as the participants of this conference. Thank you, Professor Kalyan.
Yeah. Hope to visit you soon.
Yeah.
So I will stop sharing now. Yeah.
Professor Michelle.
So
I think
Michelle has not joined, then she can invite Professor Swaminathan.
Yeah, okay. Ma'am, can you please invite Swaminathan? Swaminathan sir is already there.
Can you introduce him if you have an introduction about?
No, ma'am, I have already done, so you can straight away go to, because he has already chaired one session.
Okay. So Professor Dr. Swaminathan, it's an immense pleasure for me to meet you here and listening to your talk, and knowing the things which you are recently doing. And I'm sure that the talk which you are going to deliver today is going to benefit the students, participants, research scholars, faculty members, in fact all of us, for doing more and more work. And I still remember Professor Swaminathan. He visited Aligarh and he attended one conference in Aligarh Muslim University on analysis and applications. And then he also happened to be a PhD examiner of one of my students. And he suggested so many things. And the most important thing is that he has given us an idea that whatever functions or whatever polynomials we are introducing, it is the time to think about the special properties which they are satisfying. So I am really honored, and I'm really glad to chair this session of Dr. Swaminathan. So I welcome Dr. Swaminathan to enlighten the audience and participants with your wonderful mathematical research and talk. So Dr. Swaminathan, please, can you start your talk now? Is he here? Dr. Swaminathan? I don't know whether he is here or not. Dr. Dilip,
Yes, ma'am.
is
Professor
he here?
Swaminathan is already there.
Has he
Professor
joined
Swaminathan-
now?
Yes, he has joined.
Okay.
Let me check. I was, yeah, he's there. Professor Swaminathan,
He's in the room.
maybe he's in the room, but I don't know why.
Is he here, Dr. Ahmad Ali?
I'm just calling him. I think he is in here, maybe not on the system.
Hmm.
Hello.
Yes, sir.
Hello?
Yes,
Yes,
Swamin-
yes. Yes,
Swaminathan, sir.
yes, sir.
You are audible. Can you share screen?
Yeah, just give me a second, okay? Hmm. Yeah. Is my screen visible?
Yes, yes, everything is fine.
So shall I start? Yeah.
Yes.
Yeah. Thanks, Professor Subikan, and thanks to ICSFA for giving me this opportunity to speak, and thanks to the Department of Mathematics, Kerala University, for giving me this opportunity. So I just keep being part of this, and anyway, so the topic is basically on polylogarithms, its integral representation and polynomial mappings. So not a very pleasant talk, I felt. So anyway, I'm just trying to give this. So basically, the contents include some information between generalized hypergeometric functions and polylogarithm. There is something called the comato-integral operator and the polylogarithm, how it is related. And there are some small information about the peak functions and my further information that I'm planning on polynomial mappings. These are my table of contents. So initially, we know that what is a generalized hypergeometric function, but still I'm giving it here mainly because I just want to get used to this notation here. So there are the parameters, there are p parameters in the numerator and the q parameters in the denominator. And we know several information about this generalized hypergeometric function. So I don't want to speak much about this, these things at this stage. And of course, it goes with the by the definition of Pochamer symbol. And we start with the definition of this polylogarithm, which is quite known. And I take this particular definition, LP of z, where it's k run from 1 to infinity, z power k over k power p, is true for all mod z less than or equal to 1. And note that when p is 1, it is the well-known logarithmic function. And for z equal to 1, this precisely speaks about the Riemann zeta function. And of course, when we speak about the polylogarithm, one of the best results so far known geometrically is that this one maps the unit disk to a domain that is convex in nature for all alpha greater than or equal to 0 is the best result so far available about this. And further geometric results are not as strong as this result. This is the best result so far. So I'm interested in speaking about the generalized polylogarithm, which is generalization of the polylogarithm with much more parameters. So where we have this as a series of the form akzk with the summation k running from 1 to infinity, where a1 is 1 and ak is going to be all the values of this form. The ratio is 1 plus a power p times 1 plus b power q over k plus a power p times k plus b power q. This is for all k greater than or equal to 2. And of course, when we look at the denominator, it's very clear that the denominator should not be 0. So k plus a is not 0, k plus b is not 0. For all pq belonging to the complex numbers with the condition that real part of p and q positive. Of course, if either a or b is equal to 1, then it basically reduces to minus 1. It basically reduces to the identity function. And in particular, if a and b are 0, then we take p plus q as r, which is basically the polylogarithm, which is the one which has been defined before. So instead of 0, if we take them as some particular value alpha, then it is basically called the function which is a large transcendental function, and it is basically a generalization of Hurwitz's function and the Riemann zeta function. So these are some special cases. So this generalized polylogarithm consists of several special functions in itself. So I'm interested in studying about this generalized polylogarithm. And when you study here, there are some properties which I want to take it from the hypergeometric function. So the relation between generalized polylogarithm and the generalized hypergeometric function is given here. So in the hypergeometric functions, if you take for all a's, for the numerator parameters, if we take for I equals to 1, we take it as 1. For all other values up to p plus 1, we take it as 1 plus a. And beyond that, up to p plus q plus 1, we take it as 1 plus b. Similarly, for the denominator parameters, if we give this value, then for all pq belongings to the natural numbers, this generalized polylogarithm is related to the normalized hypergeometric function. When I say normalized to generalized hypergeometric function, it means that it takes the value 0 at origin. So these are the information we have. So from this generalized polylogarithm, I am interested in speaking something about the Komatsu integral operator. So we just give you how this construction goes on. So let us consider the integral representation of the gamma function. So now we replace the parameter t by some n plus a times u, so that we can write it in this particular format. So once we write this in the format, and then we try to multiply both sides by z power n, and just we go back here, we try to multiply with z power n, and then try to take a series summation of the series, then making some suitable change in the variable, we get precisely this left transcendental functions representation, which is precisely given here. This is basically called the Komatsu integral operator in function theory. This integral operator has got several interesting properties, and it is studied in function spaces in a nice way. We'll just to give some information of it shortly. And multiplying the resultant and replacing a and b by p and q in the above integral representation, we basically get this double integral, which is basically the integral form of the generalized polylogarithm, and it is basically called as generalized Komatsu integral operator. And please note that for getting this integral representation, there should be some adjustment or compromise should be made on the parameters. So all these parameters A, B, P minus 1 and Q minus 1, they all should be the complex numbers which are greater than minus 1 in their real part. So only this is the one condition required for making this particular integral representation. So of course, from this integral representation, we try to write it as a generalized Komatsu operator. So where we are writing it as when A is not equal to B, we have this particular format. So this integral can be adjusted. And when A is B, we are trying to get, because rather than this double integral, we can try to convert this into a single integral and we'll be able to make this information. So this is basically the generalized Komatsu integral operator given by this form. So once we have this generalized Komatsu integral operator, please note that when A equal to B, this is the Komatsu operator given here. This is quite well known in function theory stories, where we give this notation for the functional L of eta over F as phi of AB, phi of PQ times ABCZ, convolution F. When we say here the convolution, what we precisely mean is this. So we take F as a function with the convolution, with the series expansion Z power n, G as a function with the series expansion Z power n. Then this convolution, this we mean that basically it is going to be something of the form an, b, and z power n. So this is what the convolution is. It is basically very clear for mod c less than 1, and for on other disk there is some slight modifications required. This convolution is basically, what we have is basically called Hadamard convolution. This Hadamard convolution is different from what Cauchy convolution we have. Okay, so now we go to the lambda t which we had earlier. So this particular part, if I take this particular part from this information, if I write it as lambda t, then this integral operator is quite well known in the in function spaces, particularly in potential theory and all. So this particular integral transform is known as, is a particular case of the generalized Komatsu operator. This Komatsu operator has got a lot of interesting properties. It makes a lot of geometrical representations. One of the important geometrical representation it makes comes from this analytic class. Let us take a class of functions which are analytic. Here F is an analytic function or the holomorphic function in the complex plane. So once we have a holomorphic function in the complex plane, then when we have this class of functions, for this class of function, we have a nice interesting property which says that whenever F is going to be in the class which was given before, then this particular convoluted operator, which is the Komatsu operator, for this Komatsu operator, this maps the unit disk onto a domain which is star-like with respect to origin. So this is a particular situation of the convex, because when we say star-like with respect to every point, it is becoming convex. So we were able to prove that for this Komatsu integral operator, we were able to prove that it maps the unit disk onto a star-like domain with respect to origin, which was a comparatively a better statement, but with the condition here that there are conditions on A with these properties. There are some conditions on A here. This is the problem, because the result of Lewis was not having any further conditions except a condition on P, which clearly says that for all P greater than or equal to 0, he was able to get the result. Whereas in our case, we were able to get, because we are trying to go for a more generalized setup, we are trying to find this with only for some particular ranges. For the remaining ranges, we have not found any result so far. So this is, in fact, after the 1983 result of Lewis, this was considered to be one of the more general results available for finding the geometric properties related to the polylogisms. So this is the information. So the question is, why we are having integral representation? What is the use of integral representation? Of course, one of the best answers is identifying the members of big functions. Big functions, again in function theory, one of the strongest one, which is playing a vital role in studying orthogonal polynomials. So I will just give some information about big functions. Before giving the information, it is having its applications in several topics, including function theory, where a lot of geometric properties are studied. And another one is in topology, when people want to study about the wake topology, which is the weak topology in the dual space, or in some functional equations like Feigenbaum equations, or in stochastic process, where we speak about the birth and death process. So in all these situations, these big functions plays a vital role. So now the question is, what are big functions? precisely speaking, a peak function is a holomorphic function on the upper half plane, and basically these functions map unit disk in the upper half plane onto the upper half plane. This can be extended to the whole complex plane except the real line, and holomorphically this analytic continuation is possible, but except on the real line, but origin is included. Origin is only the common point, and they have an integral representation precisely of this format, where this mu is a non-negative modal measure satisfying this condition. So this is precisely the definition of peak function given in the book of the classical book of Donog about the peak functions. Of course, as I said, peak functions have got a lot of applications, so people are interested in speaking about these peak functions. Now, but anyway, if I'm giving you a function and ask you to see whether it is the class of peak functions, it is difficult to find. In fact, it is too difficult to have such an integral representation. So we need to make a change. So we need to find some other alternative. Of course, this alternative are given in the literature. Just we will try to highlight this. In one point is the peak functions are taken as reciprocal of Stieltjes functions. So there were some Stieltjes function where reciprocal is taken. Peak functions are considered to be the reciprocal. So one of the good example is this function. So once we have this function, the numerator is a special function, denominator is a special function. With these cases, as these special functions can always be related with the other several special functions, there was a fine question that can we speak this as the ratio of some hypergeometric functions? This was the question available here. So to answer this, we go to the work of HS Wall, from where we'll get some lead. The point is, let AK be a sequence of non-negative real numbers with A0 be 1, and this AK satisfy this particular moment equation. AK equals integral 0 to 1 t power k d mu of t, where mu is the probability measure on 0 to 1. So we take all such moments and we try to form a series for which these AKs are coefficients. So this series will precisely have an integral representation of this form. So f of z is going to be such a series, and these moments are basically called Hausdorff moments because we are taking the interval between 0 and 1. So these are basically called the Hausdorff moments. In fact, this f is considered to be the generating function for getting these moments. So, and of course, once when we have this AK as a sequence of non-negative real numbers with A0 equal to 1 in this Hausdorff moment sequence, this implies that these AKs are basically called completely monotone sequences, or every completely monotone sequence will give us Hausdorff moment sequence. In fact, what is a completely monotone sequence? Basically, the difference, what we are trying to find, is going to give us greater than or equal to 0. So another difference is going to precisely give us this information, is what completely monotone sequence. So when they are going to be completely monotone, the corresponding AKs are called as Hausdorff moments. So this is one information. Now I was talking about peak functions. Suddenly I'm jumping into Hausdorff moments. I will just tell you what exactly. F, which is given by the peak function here. The F which is given by peak function here, basically this one. Here, from this information, we try to get some more stories here, and we are trying to take this capital F. For this capital F, they are generating function for the Hausdorff moment sequence, and consider a set of all such F. We call that set as T, and precisely this class T is holomorphic in the slit domain, where the slit lies between 1 and infinity. So this is holomorphic everywhere, and T is available in the set of peak functions. So to find whether a function is going to be in the class of peak functions or not, if at all, we take the function, and if we are able to relate it with the Hausdorff moments, then we will be able to, if the series expansion, and precisely if the coefficients of the series expansion are going to be the Hausdorff moments, then that should be in the class of peak functions. Or much more information is required that we'll speak. For that, we will take this G sequence. Basically, we call it as a G fraction. We will consider this particular type of a G fraction, which we call it as a G sequence. And here there is a known result which is available in HS Wall as well. For a sequence AN, we have this, the following statements are equivalent. First is the sequence AN is a totally monotone sequence. Totally monotone means whatever is given here, this is what we mean by totally monotone. And whenever it is a totally monotone, it is equivalent to saying that it is a Hausdorff moment sequence. And if it is Hausdorff moment sequence, when we take the function AN with this property, any such series AN which is holomorphic, or which is given the series expansion for the holomorphic function, this always have a G sequence expansion, and analytic continuation completely. So this is basically what we have the information here. It means that when we have a Hausdorff moment sequence, I already told you it is going to be the class of peak functions. In fact, so what we are trying to precisely say is you have a sequence which is either totally monotone or it is a Hausdorff moment sequence. If you have any one of this information, from there you will be able to precisely get the class of peak functions. So the other way is, if at all you take a function, if the function has a G sequence expansion, then it is going to be the class of peak function. How to find a G sequence expansion? To find a G sequence expansion, the best way is to find this particular type of representation. So this representation is much easier than the original representation of peak functions. So we'll go back to the well-known story where we take the 2f1 Gaussian hypergeometric function, and one of the known case of this one, which is given in the monograph of HS1 on the analytic theory of continued fractions, it is given that the ratio of this is going to be in this series precisely. In fact, it was in fact mentioned by Professor Bhargav in his talk also, such ratios, and here precisely these ratios are going to have a G fraction expansion available here. So once these are going to be the G fraction expansion they have, it precisely means that they are going to be in the class of peak functions. So it is precisely given that they have this particular integral Stieltjes representation. Once they have this Stieltjes representation, they are going to be the class of peak functions. So this is what precisely given. Only one small information which I am missing is it is true for all Z in the unit disk. So this is only information I am missing here. Now, when we want to speak about the peak functions, of course, when we want to speak about peak functions, there was one more information given by Oliver Roth, Rushava, and Salinas, that let us take the functions f and g to be in the class of peak functions. Then they have a representation of this particular format. So once they have this particular representation of this one, then their ratio is also going to be in the class of peak functions. So this is what given by them, of course, with the extra conditions that these phi and psi are basically non-negative Borel functions, and that phi by c is going to be an increasing function. So if at all phi by psi is going to be an increasing function, then they are going to be in the class of peak functions. This is what they have given there in the result. So taking a lead on this, they proved another further result is for all alpha between 0 and beta, the ratio L of alpha over L of beta, where this is a polylogarithm. For such polylogarithm, they have proved that they are going to be the set of peak functions. This is what the proof that these people have found using the Hausdorff moment sequence. So taking a lead on this with some numerical values and some mathematical software, I was able to get some particular values where I was able to get some particular values that precisely says that these are going to be in the class of peak functions, which is a generalized polylogarithm. So my entire question was to prove this particular result so that it helps in studying several further results. So, and in fact, I was able to go for a particular case. I took P equals 1, Q equal to 1, and I took this particular situation, and I was able to get that it has got an integral representation of this particular form. So once it has got this integral representation, for this integral representation, I was with Paco Marcion, I'm working on this particular one, where whenever this B2 minus A2 is greater than or equal to B1 minus A1, which is going to be non-negative, and A1 minus A2 is going to be greater than or equal to B1 minus B2, which is strictly positive, then this particular ratio is in the set of peak functions. So this is what one result which you have proved, and the proof was quite simple. We take f as one of these functions, the numerator function, and g as a denominator function. Of course, the particular case when A1 equal to B1 and A2 equal to B2 is easy to check because that follows from the result of Roth, Rushava, and Salinas. So, of course, hence this reduces the story into A1 minus A2 positive. So, what we are trying to say is we are interested in checking only one part, that because in their result of them, what they have tried is they try to take this as increasing. So, they want to prove that with this increasing condition, they are able to prove this case. So, taking a lead from there, precisely what we did is we want to prove that only this particular term is going to be increasing. Once, if you prove this is increasing, the story is done. Of course, this is obviously true for A1 greater than or equal to 2, A1 greater than or equal to A2. And for the other case, again, by using the lemma, means the result of Roth and Rushava, we are able, it is enough for us to prove that this particular function is increasing. And to prove this function is increasing, we are trying to take the logarithmic derivative. And after taking the logarithmic derivative, since each f of t is positive, and for all t between 0 and 1, we are trying to prove only one particular part, which is going to be given in the right hand side, the last term. So, which we are able to get it here, and we are able to prove this result. So, of course, for that we have some straight equations, and using this equation, we were able to prove this result. So, once we are able to prove a particular case is true, then we want to do it for the other generalized case also. And for other generalized case, we were able to get some graphical illustrations and numerical values. Mathematical things is not so clear. So many places we have used the graphical illustrations and the numerical values to obtain this result, which is a much more general result, but with a particular range where it is going to be true. Now the question is, why I need to prove all these things they are going to be in the class of functions? Because I'm interested in studying much more general story than what is given here. I'm interested in studying that. So what is that? So it is about the continued fractions and the polynomial mappings, which are of my interest. Precisely, we know what is a continued fraction is. Basically, this is what the continued fraction given here. And of course, it converges if the sequence of its approximants precisely, where an is called the canonical numerator and bn is called the canonical denominator. And if at all fn converges as n tends to infinity, then we can say that this continued fraction expansion converges, and all this information are known. And this fn is called the nth approximant. And if, of course, if this particular continued fraction diverges, if such limit does not exist, all these stories are already available about this continued fraction. But what we are interested is, we are interested in the result of Sivojic and Klinovsky, where they proved this generalized polylogarithm for particular integer values. Here note that whatever is given here is an integer value. They have proved that for such particular integer values, they have a particular continued fraction expansion. And this continued fraction expansion have the conditions. An of 1 is 1. For all other values, for the even numbers, you have a particular range, and odd values is going to be something. So these are the things precisely they were able to get it, and they were trying to prove this particular result, where these ans and bns are given by particular value, given in the paper referred here, and this continued fraction converges and represent only a single branch of the analytic function. So this single branch helps us to study several properties, and this single branch also comes from the story of big functions only. So once we have this information, this was obtained using the classical Stieltjes technique. Once we have this classical Stieltjes technique, we are able to proceed further. And in fact, their result is much more general than, because for n equal to 1, it is the well-known equation of the logarithmic function. Other results were also obtained by them. So in fact, they proved that their result using some nice software techniques, and proved and found the speed of convergence, and all this information were given in their paper. But only problem is they were able to do only for integer values, beyond which they were not able to study. But if at all we try to study this for much more in a general setup, we will be able to get much result. But finding a continued fraction expansion for generalized polylogarithm is not easy. However, if at all we find the corresponding peak function representation, from the peak function representation, we will be able to get the corresponding Stieltjes representation, and the Stieltjes representation can give us a lot of information. What is the information the Cauchy-Stieltjes representation gives? It basically can give us to unwrap the measure, because if S lambda is the Stieltjes representation, by taking such a polynomial mapping, we will be able to unwrap the measure from a finite set or from the half interval to the whole interval. So such a unwrapping of the measure makes a lot of study in orthogonal polynomials, particularly speaking about the spectral transformations, as well as speaking about the tridiagonal matrices and all these Jacobi matrices and all these studies. So this unwrapping of the measure generated the study of polynomial mappings. So what we are interested in is taking the polylogarithm, and from there trying to get the Stieltjes representative, the peak function representation. From the Stieltjes representation, unwrap the measure. From the unwrapped measure, try to construct an orthogonal polynomial. And of course, only condition is the orthogonal polynomial which we construct in this procedure need not be unique. So this is what has been given. So we were trying to use the same thing, So we are interested in doing it for the generalized polylogarithm. So once we take it for the generalized polylogarithm, the corresponding blocks are basically the spectral transformation blocks coming from here. Each of these blocks have got nice and interesting properties as given by Maximum Derevian, and we followed the same procedure and we were trying to do it for the generalized polylogarithm. So once we do it for the generalized polylogarithm, instead of this particular unwrapping, we have taken the unwrapping with reference to the related, J fraction expansion, which is following from the G fraction, and we were able to prove that the numerator and denominator of this equation, the question mark is basically this equation, the numerator and denominator satisfy this particular type of three-term reconciliation. And we all know that whenever all orthogonal polynomials satisfy three-term reconciliation, and Favart theorem guarantees that always three-term reconciliation implies orthogonal polynomials. So from a given generalized polylogarithm, using Stieltjes measure, we are able to construct new type of orthogonal polynomials. So that is what the polynomial mapping helps us to get this. So these are the new ideas which we have done here. We are proceeding further.
Professor, I think, okay, you have finished it because the time is finished now.
Yeah, just I'm also finishing. That's why I was going a bit fast and just I finished it. Yeah.
Okay.
Thank you.
Thank you, Professor Swaminathan. I personally admire you for taking that aspect of special functions, which makes it different from others, because there is a usual impression that the people who are doing special functions, they are just doing computations, introducing polynomials, but you are the one who have taken it to other heights, and by relating it to geometric function theory, and then by studying the properties of these functions. And particularly, I like the idea which you have taken when you have taken a pig function, and then you have taken it as the reciprocal of Stieltjes function, and then you said that this is the ratio of two special functions. So these are like some very simple but very important results. And of course, I am sure that your views and your research is keep on motivating the people like us also. And I still remember, and I have quoted this also, that you always motivated that we should go for that aspect, that is just not only introducing the things, but to see their properties, and especially the geometric properties, and to relate them with analysis. This is really making it the field of special functions more important. So thank you for this enlightening talk, and thank you for making the field of special functions more reachable and more applicable, and of course more important. Thank you, Professor Swaminathan, for a wonderful talk and for the work which you are doing. Thank you very much.
Thank you. Thank you.
Thank you, Professor Swaminathan, for
Yes, thank you.
your enlightenment talk. Professor Sugi, we have Michelle. Okay. So,
sorry, is it possible to ask a question or not?
Yes, you can.
Yeah,
Oh,
you can ask now.
Professor Karp, good afternoon. It's after a long time. Yes, I still remember in Chennai, I think we met.
Now you met.
Well, we met in India in 2004 first.
Yes. It's nice seeing, and I hope that the things will get better and we can meet face to face also. But anyhow, it's also nice, and I think credit goes to Dr. Dilip and Dr. Ahmed Ali for arranging this conference, and for providing us the opportunity to at least see and meet all of you in online platform.
Okay, Swami, this generalized polylogarithm you showed with some 2 or something parameters, this is a ratio of F32s, correct? Or F21s?
Yeah, F32s, yeah.
F32s. Okay, it's more like a comment. Have you seen our recent 2 papers with Alex Dyachenko about ratios of Gauss hypergeometric with shifted parameters? you may take a look.
Yeah,
We-
okay,
we don't-
definitely. Okay.
We don't have F32s there, but I have some unpublished result, which I think I presented in some also online conference with some particular ratios of more general hypergeometric if they
Okay.
belong to Stiltius class and stuff like that. So,
I'll definitely
well,
have in contact. Yeah, definitely.
yeah.
Yeah.
So
That will be
yeah,
useful
and
for us,
in this more general setting, I also used the same lemma that you showed by the Roth, Rushevai, Salinas,
Yeah.
but not in the paper with Alex Dyachenko. But you may take a look because we weren't interested in polylogarithm in especially, but it's just ratios of hypergeometric with shifted parameters, and polylogarithms are particular cases as far as I can understand.
Yeah. So I'll send you an email so that I'll discuss to you about that.
So,
Yeah.
well, if you need to send me a letter, I'll send you a link.
Yeah,
or
definitely.
just look at my homepage, you will see
Yeah,
it.
definitely. Okay. Yeah.
Thank
Thank you, Dimitri. Yeah. Yeah, thank you, Professor Subikan, and thank you for your nice words. And thanks, Dr. Dilip, for arranging such a nice, excellent conference, wonderful conference with Dr. Hamadul. So, shall I unshare my screen?
Yeah.
Yes. Professor Michel.
Yes, I am here.
You please share your screen.
I share my screen. Okay.
Yeah.
For us, it is good afternoon, Professor Miss Smith. And I used to follow you on Facebook. So
Oh.
I think you have shared the text editor, not the
Yeah.
slide.
Do you see my screen?
Yeah, I can see.
Okay, good.
But we could see the LaTeX file, right? Not the
Okay, good.
slides.
So you tell me when I can start.
yes, you can start. I think there is some problem in my Zoom. And yes, it's okay now.
Okay, so I can start now?
Yes, Professor Walsh Smith, you can start your lecture now.
So the first thing is that I just received the message telling me that my talk is now, but it was agreed with the organizer that my talk will be tomorrow. So I did not know that I was going to speak immediately. And my plan was to use my Blackboard at home, but I am not at home, and I do not have the camera to use my Blackboard. So what I will do is to use some slides, but they were not prepared exactly for this purpose. Anyway, let me first thank the organizers for the invitation. I am glad to have the opportunity to speak again to this international conference on special functions and applications. So if you see December 23, it's not a misprint, it's really what I thought it would do. So the abstract of my talk is the following. According to the classical theory of Wheatstone interpolation, an entire function of a single complex variable having exponential type less than pi is determined by its derivatives of even order at 0 and 1. And I plan to explain the generalization of this theory to several variables. I would like to start by telling you what are my connection with the conference on special function and their application. The first time I participated was in 2016 when I gave the RP Agraval Memorial Lecture. This was my first opportunity to participate to this conference, and I enjoyed so much that I participated several times after that. I could not come in 2017, but I was there in 2018 for the conference, which was in Kottayam in Kerala. And this was quite important for me, not for the lecture which I gave on linear recurrent sequences, but for the fact that I was the chairperson for the talk by M.A. Patan on generalization of Taylor series, Riemann zeta function, and Bernoulli polynomials. And this is the place where I learned about Liston polynomials, Liston interpolation. And since that time, 2018, so 3 years ago, I have been quite busy with this topic. I participated also in the conference in 2019, where I gave a lecture in Bikaner on Liston series, generalization, and arithmetic application. So I already explained 1 year after the 2018 conference what were the arithmetic application that I had of Liston interpolation. But I will not speak of arithmetic today. I will speak only on the theory. So now I am participating to this conference where I will speak on Liston expansion in several variables. The file of my talk is on my website, and you have all the information. In particular, you have information on the slides of the talk which I gave on multivariate Liston interpolation for the conference of the Indian Mathematical Society. It was on the 4th of December. And so you have slides for a longer talk. And also, I gave a course in Chennai in December on Liston interpolation. In the first talk, I explained the theory in one variable. In the second, it was in 2 variables. In the third one, in several variables. And in the fourth one, I gave some expansion of functions of finite exponential type. So this is the introduction to my topic. And I have written 2 papers very recently. They are not yet submitted. The comments are welcome. One is for univariate and bivariate Liston interpolation. And the second one is on multivariate Liston interpolation. So I am currently finishing these 2 papers, and I will submit them very soon. But if you have some comments, I am very much interested to get your feedback. So I expected I would just go on the blackboard after this introduction, but I will use some slides which were not prepared exactly for this talk. So I will go rather fast on some slides. The problem of Liston interpolation is the following. If you have 2 sequences of complex numbers with the indices which are the even integers, it's convenient to write the index t and not 2k, for example. We write t is an even integer. So we have 2 sequences of complex numbers, at and bt. And the question
Sorry, we do not see the slides.
You do not see the slides?
We just see some LaTeX source piece. We don't see any slide.
I think, Professor, you have shared the source file, text file. So,
Okay, so
please share the PDF.
okay, let me try again.
Only the source
Let
file
me-
is.
Let me come back to okay, let me so you did not see the slides which I had shown before?
We could see only one slide, and that was, I think, source file.
Okay. So
A page of LaTeX.
Okay, let me just come back.
Can you share it once more so that
Okay,
hope you
I
know
start
that-
again.
yeah. You just open the PDF file first and then share. Then it will be nice. First you open the PDF file,
Okay, which I
then
this
come
is what I
back
did.
to the browser and then
Okay,
share.
now
the-
it should be okay.
Yeah, now it is
Oh.
fine.
Now it's okay.
Okay, I am sorry that you did not see all the slides before.
Mhm.
So let me say that you get all the information on this website, which is my website, and there you will find all the information there. So I explained my participation to the conference in 2016 to 2018 with the talk by M.A. Patan, 2019, 2021.
Professor Michel, can you make it full screen because some part is missing, some part is breaking. I think. Can you make it full screen because Control L, Control L.
Like this?
Yeah. Now it is fine. It's fine.
Okay. And so what I said is that on my website, you will see the slide, the video and the slides of a course which I gave at the Institute of Mathematical Science in Chennai. It was earlier this month. And these slides and the links to the video are on my website. And as I mentioned, I gave 2 lectures on, I wrote 2 papers which are on my website, which are not yet submitted. So if you have some comments, they are welcome. The first one is on univariate and bivariate Lidstone interpolation, and the second one on multivariate Lidstone interpolation. Okay, so the problem of Lidstone is when you have 2 sequences of complex numbers with the indices which are even integers, does there exist an entire function such that the derivatives of even order at 0 and 1 are the given numbers AT and BT? And is such a function unique? So I will go rather fast on the case of one variable. The case of one variable is that if you have a polynomial with the derivatives of even order at 0 and 1, which are 0, then the polynomial is 0. This is the basic fact on which is the start of the theory. So here I have several proofs. There are several proofs of this result, which is quite easy. And the consequence is that there exist 2 sequences of polynomials, lambda t0 and lambda t1, such that any polynomial can be written as a finite sum, where you have the derivative of even order at 0 and 1 times these polynomials, lambda t0 and lambda t1. So these Lidstone polynomials have the property that they take the derivatives of even order at 0 and 1 are 0 apart from the derivative which correspond to tau 1 and t1 or tau 0 and t0. So the notation which I am using is not the classical one. The classical one is lambda k for what I denote as lambda. So when k is even, I denote it by lambda t1. And the polynomials of Lidstone are usually denoted by lambda t, but for me, they are lambda t1. And the polynomial which I denote by lambda t0 are just lambda t1 of 1 minus z, or lambda k of 1 minus z. But for me, it's convenient to have 2 sequences of polynomials, because in several variables, I have several sequences of polynomials. So we have some values of the Lidstone polynomials, which are known. And what will be important for the generalization is that we have an inductive formula. If you write the characteristic polynomial of the polynomial lambda t for z to the t plus 1, you get a formula which gives an inductive way of computing lambda t1 when you know the lambda tau 1 when the tau are less than t. T and tau are even integers for me. And the same argument using zt over t factorial gives you a formula which gives lambda t0 in terms of the lambda t tau 1 for tau less than t. So we have inductive formula for these polynomials. I will discuss the order and the exponential type of function. The only thing to know is that the function exponential of zeta z has an order 1 because the exponent of z is 1, and the exponential type is the modulus of zeta. An important result of Poritsky is that an entire function of exponential type less than pi, which has all the derivatives at 0 and 1, 0 for sufficiently large t, is a polynomial. And this is a consequence of an expansion due to Poritsky. Any entire function of exponential type less than pi can be written as an infinite sum of ft of 0 and ft of 1, where the t is an even number. So I go fast because what I want is to explain that this is true, this holds in several variables. Using the result of Poisky, one deduces the generating series of the Liston polynomials. And in fact, we can prove this generating series directly. And this is the way to prove Poisky expansion formula and using the inverse, the Laplace transform. And finally, to complete this survey of one variable Liston polynomials, there are some results of Schoenberg on the unicity of functions which have the derivative which are 0. These functions are linear combination of sine of k by z. And Buck gives a more general development for entire function of finite exponential time. Okay, let me go to two variables. So I work with two variables. I have the derivative dt, which is derivative with respect to z1 t1 and with respect to z2 t2. There are very few references on two variables, but they do not enable the development which I will explain. If we use the Liston polynomials in one variable, we deduce an expansion involving the derivatives of even order at 0, 0, 0, 1, 1, 0, and 1, 1. But such an expansion is not exactly what I want. And I just want to explain what is the solution which I propose. I will take 3 points. E1 is E0 is 0, 0, E1 is 1, 0, and E2 is 0, 1. And I will take the derivatives of the function of two variables with respect to the t, which is t1, t2, with the length which is even. And for the two other points, I request that t1 and t2 both are even. So I take more points, at more derivatives at 0 than at the two other points. And the argument which I explained here is that this gives the right condition for the number of equations and the number of unknowns. So the unicity result is the following. You take the 3.00, 10, 01. You assume that a polynomial has all the derivative which vanishes at 0, 0, 1, 0, and 0, 1. For t, we just at 0, we ask that the length t1 plus t2 is even. And for the two others, we ask that t1 and t2 are even. And then we have the unicity. And because we have the right dimension for the right values for the dimension, we deduce that there exist families of polynomials, lambda ti. I take the value 0, 1, and 2, and ti is in the set T which I described. And there is a unique family of polynomials lambda ti, such that d tau of lambda ti of ej is the Kronecker symbol, which is here. And so this is the generalization in two variables. And from this generalization, we deduce that any polynomial can be expanded in a unique way as a sum where you have the derivatives of f at ei for ti in t times these polynomials lambda t0, lambda t1, and lambda t2. So this is the generalization in two variables. Now we can follow what we did in the case of one variable. We write these special polynomials and we expand them. And using this expansion, we deduce some formulae for the lambda t1, lambda t2, and lambda t0, which are inductive formulae. And so we can follow what we did in the case of one variable. We can extend to finite exponential type. We first have the unicity result. that if a function of exponential type less than pi has all these derivatives which are 0, then this function is 0. We can prove this by induction, by using the one variable result, or we can use it by using a more general result which extends the result of Poritsky, which is that any entire function of exponential type less than pi has an expansion with the derivatives of f at ei times these polynomials lambda ti. And the series is absolutely convergent. If we look at the special case of this result for the function exponential zeta z, we find a formula which gives exponential zeta z as a series with these polynomials lambda ti, exponential zeta I z to the t. Okay, I will maybe, I know that the time is a little bit over. I just say that we can deduce some formulae for the generating series of the functions. And from that, we can deduce explicit formulae for the two variables Lidstone polynomials in terms of the one variable Lidstone polynomials. Okay, so this is the result for exponential type less than pi. We can deduce the result. And for function of finite exponential type, we have a unicity result, which is the analog of the result of Schoenberg, and it works essentially the same, apart from the fact that we do not have constant here. We have entire functions of a single variable of exponential type less than tau. And then we have an expansion, which is the generalization of the result of Buck. Okay, so I don't know, because the time is a bit out. I don't know whether I have still some time to say more, or do you prefer that I stop?
I think you may take 3-4 minutes more, Professor.
Okay, so I just tell you what is the generalization in several variables. For two variables, I had 3 points, 0, 0, 1, 0, and 0, 1. For n variables, I take n plus 1 points. The first one is the origin, and next, E1, En is the canonical basis of Cn. So it corresponds to 1, 0, and 0, 1 for n equal to. And the result, the solution which I propose is to take the derivatives dt, where the length of t is even at all the n plus 1 point. There is no further restriction at the origin. For E1, there is a restriction that T1 is even. For EI, we ask that T1, Ti are all even. And so for En minus 1 and En, the restriction is the same, all the Ti are even. So let me just say that with this definition, we have a set T, which is defined by the condition which I gave. We have the unicity result, and we have the existence of the polynomials lambda Ti, which take the values which are the Kronecker symbol, and therefore any polynomial can be expanded as a finite sum with the derivatives dt f of ei. And so there are some more slides, but I can just give a summary saying that everything which is known for 1 and 2 variables works in the same way for several variables. Okay, so I think I should stop now. So thank you.
Thank you, Professor Michel Warsmith, for an interesting talk. And I have certain queries, or just I want to, I'm really honored to listen to your talk. And there are certain things which just came in my mind, that you have taken the Lidstone polynomials, and is it possible, like when we have taken two variable form of this polynomial, so will there be some interesting results if we take the variables to be complex conjugate? This is my first query. And also, is it possible that we may add one parameter, or maybe something related to the matrix to form a system of like system of these polynomials, or to see the equations, to see these polynomials as the solution of equations. Is it possible to do something in this direction? Like,
Yes. Thank you very much for your kind words and for the two questions. For the first question about complex conjugation,
yes.
when I gave my courses in the Institute of Mathematical Science, there was a question which was asked to me by Pure Sotam whether we could do the same for any field instead of the complex numbers.
Okay.
And I thought to that. And in fact, for the polynomials, it's clear that we can take a field of characteristic 0. There are some denominators, so characteristic 0 seems necessary. Now, we can go a little bit further. When we have some generating series, we can look at formal power series. And in this case, it works for any field of characteristic 0. Now, you ask about complex conjugation. It's clear that if I consider exponential type, this will not work in the p-adic setting because the exponential function has a finite radius of convergence.
Okay.
And so there are some specific things to complex numbers. Complex conjugation, I don't know, but I will think about it. It may be interesting to use complex conjugation. For the matrix and the set of equation, in fact, this is something which occurs in the two papers which I wrote and which are on my website. I have to solve some system of equation which have a matrix which is 2 to the n by 2 to the n. So in the case of one variable, it's 2 by 2 and it's easy. But we have a matrix, and these functions are the solutions of a set of equations. So it's exactly what you suggested.
Okay, thank you very much, Professor. And thank you, Dr. Dilip, for providing us an opportunity to listen to a mathematician like Professor Wallsmith. And I'm sure that your talk is going to benefit so many students who are attending this. And it has, of course, motivated me also to work something related, because Costabile we are following related to the determinant approach of polynomials he is doing. So I've seen one paper you mentioned with this him also, although Costabile. So maybe we will think about the determinant expression of the interpolation or the polynomials which you have mentioned. And thank you, Professor, for very nice talk, very nice word. And
yes, I am sorry that you had to shift the talk. I was not online at the right time, but I did not know it was today.
no, it was.
Professor Michel, I am extremely sorry for that. Actually, in the initial, when we are planning the session, we thought that you will be in India during this time. So we were less thinking about your timing. So otherwise, we could have done it very early. So
yes,
later on, you said that you have to go back. So it was that created a little bit confusion. I'm extremely sorry for this, and let me thank you for your wonderful session and your presentation.
Yes,
in fact,
I wanted to attend.
Yeah.
Yes, I wanted to attend the talk by Kalyan, but I missed it because I learned too late that it was today. So, but congratulations for organizing this conference online. It's very good.
Thank you, Professor. Thank you. So thank you, Subhi Khan Ma'am, for your chairing the session. And I also thank the speakers, Professor Kalyan Chakravarti, Swaminathan, and Professor Michel for their wonderful talks, which has definitely benefited the participants of our conference. And I am sure that this research will be beneficial for your future research in this area. So thank you very much, participants. Currently, we have 2 parallel sessions going on there. So those who are presenting, those who have their presentations today may please join that parallel sessions for their paper presentation. And we will be coming back at 5:50 for that R.P. Agarwal lecture by Ken Ono. So please come back. Please do come back at 5:50 for this R.P. Agarwal lecture.
Thank you very much for all the participants, and thank you once again, ma'am Subhi
Thank
ma'am, for your
Thank you, Dr. Dilip. Thank you, Professor Michelle. Thank you for giving me an opportunity to listen to these great mathematicians. Thank you, Dr. Dilip. Thank you. And by the way, your background is looking very mathematical, you know.
This is in fact, we had some technical problem here, so I shifted the place where I was sitting. Now.
It is looking more mathematical and scientific, you know. Okay.
Okay, thank you.
Thank you,
Thank you.
Professor. So we can leave the meeting now.
Yes, you can leave.
Okay. Okay. Thank you. Thank you, Professor Michelle. Thank you, Dr. Dilip.